Okay, good morning, guys. So we are going to move on to the next section in Chapter 7, which is finding the sums of infinite geometric series. So we had talked in the last section, we worked on geometric sequences and series, but we focused on the formulas that applied for the finite sum. So when you were doing a formula for the rule, you can use that for finite or infinite. However, when you're finding the sum, when you're finding a sum for a finite geometric series, you can use that formula that we had done in the last set of notes. However, obviously, if you're trying to find the sum of an infinite geometric series, it's a little bit different. Now, let's think about what infinite means for a second. So infinite means it goes on and on forever, right? So that's when we see that ... at the end of the sequence or series. That indicates that it's infinite versus finite. Now, when we're talking about finding the sum, we might be thinking, well, how can you find the sum of something that goes on forever? So this is where we get into limits a little bit. So you can't actually calculate a final sum, but you can say what it's approaching, and it'll approach some limit. So there'll be some number that it can't go above no matter what you do. So to kind of give you a little example of that and how that kind of works, see if I can fix this here. You could take a look at this little example with the piece of paper. Now, I'm not going to cut paper since I'm just virtual right now, but I will just draw examples of what that would kind of work like. So imagine that you have a piece of just regular computer paper, right? It's like 8.5 by 11, and you cut it in half. Now, that's your first piece of the sequence, right? So this is your paper, and it's like, let's say, half of a square unit, right? Because it's half of a piece of paper. So now when you take the remaining half and you cut that in half, each of these would have been 1/4 of the original piece of paper. And then if you take one of those quarters and you cut that, you would now have 1/8 of the original piece of paper, and so on. So to kind of give you a little bit better of a visual here, so let's say I have a piece of paper, and I'm going to do this, let's say, sorry, my drawing is not the best, but okay, so this is my one piece of paper. So it's 1 square unit, whatever that is. Now, when I cut it in half, that would be a 4 by 3. So half of my paper, I'm cutting that in half. So now this is half of this paper, right? Because this was 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Yeah. So this is half of this paper, right? Now the remaining half, I'm going to cut that one. And that would be 1/4. And then if I wanted to cut that one in half, I would have 1/8. And then if I were to cut that one in half, that would be 1/16. And if I were to cut that one in half, that would be 1/32. And then as you can kind of see that pattern going down, right? So now what would happen if we were finding the sums of this? What would that look like? So I wrote those numbers in a chart, right? So number of pieces of paper on the table. When I put my first piece of paper on the table, I have half of a square unit there for my area. And so the combined area, since it's just one piece of paper, is 1/2. Then when I put the second piece of paper on the table, that's 1/4, right? And then if you add those together, you have 0.75 as your total combined area or your sum. Then we had the 1/8 piece, which when we add that to the 1/2 and the 1/4, we get 0.875. Then we add the 1/16 piece, and we get up to 0.9375, then the 1/32, then the 1/64. Now, technically, I could keep cutting it, right? I could have a 1/128, then a 1/256, or whatever. But you'll notice that as you total up the sum of all the piece of papers in the sequence, the number is getting closer and closer to 1. And that's because the entire piece of paper was equal to 1 square unit. And there's no way you can cut that paper as many times as you want. It's never going to add up to more than one piece of paper. So in that situation, even though you could theoretically cut that paper for an infinite number of times, you could cut it in half, cut that half in half, cut that half in half, and so forth, until you have like a little grain of a piece of paper. No matter how many more times you can cut it, even if you were doing it on a microscopic level, putting them all together and adding them back together is never going to be more than one. So what we say is it's approaching a limit here. And because that number is less than 1, we're saying it converges. So as the n approaches infinity, and the n would be the number of pieces of paper in this particular example, but in any sequence, it's what step of the sequence are you on. As that sequence number increases, which approaches infinity, right? Because this is an infinite sequence. So as that number approaches infinity, then the sum in this case is going to approach 1. So that's an example of kind of how that would look with that piece of paper example that is in the notes that I provided for you, in case you're kind of getting a little bit confused by reading that, because reading that on your own, and you could even try this little experiment at home if you wanted to, but that's really what that table would look like when we. So it said, based on your table, what number does the combined area of pieces of paper appear to be approaching? And that's where we said it's going to be approaching 1. So it's going to be approaching 1, because you notice it got to like 0.98, 0.99, and then it would just keep going 0.9999 on your calculator and so far. Using the formula for sum of a finite geometric series, so that was the one that we did in the last unit, which was a sub 1 times r raised to the n minus 1, right? So if we were to use, oh no, sorry, that's the rule formula. We want the sum formula. Excuse me. So the sum formula for a finite geometric series is a sub 1 times 1 minus r to the n power over 1 minus r. Now, in this particular case, well, what is our r? What's happening each step of the sequence? So if I go back to my little chart here, for example, what is happening? How are we getting from one number to the next to the next? Well, how do you get from 1/2 to 1/4? You multiply it by 1/2. How do you get from 1/4 to 1/8? You multiply it by 1/2. How do you get from 1/8 to 1/16? You multiply it by 1/2. So we can see that our r is 1/2. Now the a sub 1 was 1/2, because the first cut left you with that 1/2 of a piece of paper to start your sequence with. Now, if we were to put those numbers in here, we would have 1/2 times 1 minus 1/2 to the n power over 1 minus, 1/2. Now, working that out, if you think about this for a second, we don't know what n is, so we can't actually solve it the way we were doing yesterday, or the day before, actually, whenever we did that lesson. I think it was a couple days because of the weekend. All right, so on the top here, we have to leave it as 1 minus 1/2 to the n power, because you have to do exponents before you subtract, right? But on the bottom, 1 minus 1/2 is just going to give me a positive 1/2. Now, if you have a 1/2 over here, and then you have one on the bottom of this fraction, those are actually going to cancel out, so you can kind of just get rid of those. And then we know that the sum in this case is 1 minus 1/2 to the nth power. So this would be the sum formula for this particular situation. And then, of course, no matter what number we put in here, we can tell that it's going to get closer to 1. So if you were going to try to like play around with that on your calculator and do 1 minus 1/2 raised to, let's say, 10, and then do a few different numbers. I'm going to actually load up my calculator so that I can. Okay, so let's see how the sums here look on a graph. So we already filled in the numbers on our paper on the chart on the last page and everything. I showed you how that looked. The partial sum, the sum of the first n terms of an infinite series. So like we said, an infinite series could go on for infinity, right? So there could be 1 million terms in that sequence. So when we find the sum, it's technically a partial sum because we're going to just say we're finding the sum of the first 10 terms or the first 20 or whatever amount that we're given. The partial sums of infinite series may approach a limiting value. So some of them are impossible to find a sum for or what it's approaching. Some you can find that limiting value or what number the sum is approaching. And it's going to depend on what that multiple or that R value is, that common ratio. So in the example we just did with the paper, the common ratio was 1/2. So when that common ratio is a number less than 1, then it's going to approach a limiting value. But if that R value is greater than 1, the numbers will just grow exponentially, so summing them would be impossible. So let's just take a look at the example that we just did. So if we wanted to graph this here, the n value, remember, is the number, what sequence or what term I should say we're on in the sequence or in the series, and then the sum here is what is that cumulative value. Okay, so for the first one, if I'm doing my n value, so my first number, my n, I'm going to say this is n is 1, right? It went up to 1/2. When my n was 2 on the second term, so when I added my first and my second term, I had 0.75, so that's that point there. On the third term in my sequence, which was 1/8, when I summed up those, I got 0.88, so that's about there. Then so on the fourth term in the sequence added in 0.94, and then the fifth term in my sequence or series added in 0.97. And then as we showed, if we continue this, that would kind of look like this is an asymptote. Now, it's approaching, right? It's approaching that, and this is called an asymptote. And this is the line here, y equals 1. Okay, so from the graph, the sums appear to approach 1 as the n's increase. So the higher the n value, the closer that decimal will be to the 1. So find the sum of the first 5 terms of the geometric series above using the finite geometric series formula. Well, as we showed on the last page there, we know that that formula from the notes in 7.3 with the finite geometric is this here. Now, again, because my first term is 1/2, and that R value is also 1/2, when we substitute those numbers in, they're going to cancel. So you're just going to be left with that 1 minus 1/2 raised to n. Now, if we're doing this for the first 5 terms, that n value is going to be 5. So I'm going to do 1 minus 1/2 raised to 5. When I go to do this on my calculator here, 1 minus 1/2 raised to 5 is 0.96875. 0.96875. Now, if we were going to do this for the next two, we would just be putting in, I would be putting in 2 different numbers. Okay, so 1 minus 1/2 to the 6th and 1 minus 1/2 to the 7th. So again, you can just go ahead and put those in on your calculator. 1 minus 1/2 raised to 6, and then 1 minus 1/2 raised to 7. And that would be 0.9843 and 44. I'm just going to round it there. So this one is 0.9844 if I round it to 4 places. This one here is 0.9922. So as you can see, the higher you go, the closer that number is going to get towards 1. So the sum, you would just say, is approaching 1. So basically, that's kind of the explanation as to how this would work, right? So the sum of an infinite geometric series, with the first term as a sub 1 and the common ratio of r is given by the following formula. And for some reason, it did not print out here. So let me just write it on there. It is S equals a sub 1 over 1 minus r. So the little thing that I want to tell you in addition, which I mentioned earlier, now if the absolute value of that r, so it doesn't matter if you're multiplying by a positive or a negative, but if you're multiplying by a number that is less than 1, so some type of a fraction, then you are going to say that it converges, meaning that's going to approach some number. So you can calculate the sum as a limit, converging or approaching some number. If the r value, the absolute value of it, so it doesn't matter if it's positive or negative, but if the value itself is greater than 1 or equal to 1, then there is no sum. And you would just write no sum and you don't have to do any work. So those are kind of nice, but people always forget about those. Okay, so let's take a look at the example. So for the given series, find and graph the partial sums for n values of 1, 2, 3, 4, and 5. So I'm going to make a little chart over here. So it's sort of like an XY table, right? So if I make this my n, and this will be my sum. So for n, the first term, and I'm going to go up to, I think it's at 5. Okay, so 1, 2, 3, 4, and 5. All right, so my first term is just 2. I don't have to add it to anything since it's just the first term, so that's the sum as well. Then the second one, I have 2 plus 2/3, which would give me 2 2/3. Then the next one, for 3, I'm adding up all 3 of these. So 2 plus 2/3 plus 2/9. So that's going to give you on your calculator 2.889. And if you want to do the last one on your calculator, it would have been 2.667. Then for the next one, you would be doing 2 plus 2/3 plus 2/9 plus 2 over 27. And that would give you 2.9629. And then if you add up all 5 terms, you would get 2.988. So when we go over here to plot this, everything's positive, so I only need the first quadrant. This is the x-axis is for my n, and the y-axis is for my sums. So an n value of 1 is going to go up to, well, here, actually, what I'm going to do is let's label this first, right? So since we're starting at 2, that was the lowest number, I can do one of those things where like you skip a little bit. And then I'm going to have 2, 2.1, this will be 2.2, 2.3, 2.4, 5, 6, 7, 8, 9, and that will be 3. Okay, so 1 and 2 will be right here. Then 2 and 2.67, so that's going to be maybe right around there. Then 3 and 2.889, 4 and 2.96, and then 5 and 2.98, whatever, so that's really close. Now, if you kept going, you'd notice that they're going to kind of level out here, and they're never going to get to 3. It's just going to get as close as it possibly can to 3. So 3 is that limit. So this particular series is converging towards the 3. Okay, now the reason this is a converging one is because our first term, we had the 2, but our r value was what? What was that number being multiplied by each time? So it was actually 1/3. So remember, you can get that common ratio by taking any term in the series or sequence and dividing it by the preceding one, or just by looking at it to see what's being multiplied by each time. Because this absolute value of 1/3 is greater than 1, we know this converges. And so in this case, it's approaching 3. That's the limiting value there. So you would say the sum is 3, even though it doesn't exactly equal 3, it's approaching that limit. Okay, find the sum of the infinite geometric series if it exists. So don't forget to say no sum and just move on if that's what it is. So first thing you need to find is that r value. So what am I multiplying by to get to the next number in my pattern? Or you could take any number here and divide it by the preceding term. So I know 4 times 2 is 8, 8 times 2 is 16, and so on. So I'm going to guess that I'm multiplying by 1/2 to get to the next term. And because I see the signs changing, I know I'm going to be multiplying by -1/2 each time. Now, the absolute value of -1/2 is just 1/2, and that is less than 1. So this is a series that converges. So that means we can find the sum or the number, the limiting number that it converges towards. So we're just going to use that formula way up at the top of the page, the sum formula, which is a sub 1 over 1 minus r. So my a sub 1 is -1/2, and then 1 minus the r value is also -1/2. So you end up with -1/2 divided by 1.5. And it works out to be -1/3. And I kind of ran out of space there, so I squished it in there. So that would be the limiting value that this sum is approaching. So now if we want to take a look at the next one, it's set up in that sigma notation, but you do the same thing, right? So this is just telling us this is the r value. This is my a sub 1 here. The r value is 1/4. The absolute value of 1/4 is 1/4, and it's less than 1. So we know this is going to converge or approach a limiting value. So we can use this formula. So 3 over 1 minus 1/4. So 3 over 3/4. Now, if I'm dividing 3 divided by 3/4, that's really like multiplying by 4/3. So it's converging towards a sum of 1. I said sum of 1, but I wrote 4, so sorry about that. Okay. All right, then the next one here, we have one more, it looks like. So this one here would be, this is our a sub 1. This is our r value. Again, it's a fraction, so the absolute value of that number is less than 1, so we can calculate this one. It will be converging towards something. So the sum is the a sub 1 over 1 minus the r. Since the r is negative, that will change to a positive. And then when you calculate that out, you will get 0.074 or 25 over 336. So either way, you want to write that sum. That was actually number 4 right there. Okay, and then number 3, what is our r value here? So how do I get from 1 to 3/2 or 3/2 to 9/4? So it looks like I'm multiplying by 3 over 2 each time. Now, if my r value is 3 over 2, that is greater than 1, so there is no sum for that one. So you don't actually have to do the formula because it's impossible. When the r value is greater than 1, then the sum will approach infinity and you would never be able to calculate it. It does not limit. There is no limiting value. It's not converging towards anything. Okay, so now using this strategy here, the last thing we're going to do is use it to show how we can write repeating decimals as an infinite geometric series, and then use that formula to help us figure out what is the fraction of this decimal. Now, if you have a repeating decimal and you have a fancy calculator and you can just type this in and do some buttons on your calculator, you'll get the fraction. But how would you do that if you didn't have that calculator? Just to show how that can work. So basically what we want to do is figure out what is your r value. Now, whatever's repeating, like there's 2 digits repeating here. It's like 0.18, 0.1, or 181818, whatever. So then that's going to be 0.01. If you look at the next problem, there's 3 digits that are repeating. So this time my r value would be 0.001. So that's how that's going to work. Now, as far as the a sub 1 is concerned, that's going to be your first part of that repeating decimal. So for this one, it would just be that 0.18. For number 2, that a sub 1 would be the 0.297. I'm not even going to worry about the number in front of the decimal. If it's 0, then you don't have to worry about it anyway. If it's a different number, you can just stick that on at the end as a mixed number. So once you get these 2 numbers, then you can do your sum formula with the a sub 1 over the 1 minus r. So you have your a sub 1 on the top, which is 0.18, 1 minus 0.01. So you get 0.18 over 0.99. Now, as you can see, both of these could have the decimal place moved over twice, right? So you end up with 18 over 99. Now, it may or may not be reducible, something that you can simplify or reduce. So both of these are divisible by 9. So you end up with 2 over 11 for your simplified fraction. Now, when you take a look at number 2, however, you have the sum, which is your 0.297 over 1 minus 0.001. So 0.297 over 0.999. Now, this one here is not, it does simplify actually. So we have 297 over 999, which simplifies to 11 over 37. Now, don't forget, we had this 297 here in front, so that's really a mixed number of 297 and 11 over 37. So just don't forget to put that back in if there was a number in front of the decimal. Okay, so now I'm going to go to 4, then I'll go back to 3 because 3 is a little bit tricky. So for number 4, the R value, everybody, what would that be? You got 0.146 repeating, that's 3 digits, so 001. Our A sub 1 is that 0.146. Now we're going to have this 5 out front of the decimal. We're just going to tack that on at the end. So we're using our sum formula, which is A sub 1 over 1 minus the R value. So we get 0.146 over 0.999. We can move our decimal 3 places on the numerator and the denominator, giving us 146 over 999. And there's that 5 in front. And then if that fraction can be simplified, you would, but I do not believe that one simplifies. Okay, so now the last problem, this one's a little different because after your decimal, you have 4, 1, and then the repeating starts. So we're going to actually kind of separate it there. So what's going to happen this time is that the A value, we're going to just put 2 zeros in there for a minute. And we're going to say our A value is, or A sub 1, is 0.006. Now the R value, we have to go all the way to where that 6 starts repeating. It's only one number repeating there, 666, so it's just going to be 0.1. So now we put it into that formula, right? We had to do this 0.006 here because it's the 6 that we're looking at, but it was the third number after the decimal. So you have 0.006 over 1 minus 0.1, so 0.006 over 0.9, and you could put zeros there if you need to. So now this is 6 over 900, which I believe reduces to 1 over 150. The only thing is we still have this 0.41 that we kind of just forgot about. So that's going to have to be added to that. And 0.41 is 41 over 100. Or you can just add it as a decimal, whichever way works for you. If you add it as a fraction, you're going to end up with 5/12 as your simplified fraction. And that would be your fraction for that one. So obviously here you would make these common denominators. So that would be 300 and that would be 2. This would be 341 times 3 is 123. Then you would get 125 over 300. And then you would simplify to the 5/12. And that's it. So that was our lesson on infinite geometric series and finding the sum of that. So that's it. If you have any questions, let me know. And the quizzes is your homework assignment for today. Have a great rest of your day.